I hope you all got the mail I sent. So what was written in this part of the board was needs correction. So if you wrote down what was written here at the end of the last class, that's not good enough. You have to be more careful. I mean, it's standard linear algebra, but all the same, what I wrote on the board wasn't right. But I hope the proof given in the mail was all right. Okay, so what we were doing, so we are studying chapter 3, which has to do with tori, which is plural for torus, and we will define a torus today. In particular, it is a commutative algebraic group, linear algebraic group. So what we did was two results. We can call them theorems because both the proofs are not, at least at this level, they are non-trivial. Okay, so I recall for you what we were doing. So 3.1 was about commutative algebraic groups. So if G is a commutative algebraic group, linear algebraic group, then 1 GS and GU are closed subgroups. It is true in general that GU is closed because you can put G inside GLN as a closed subgroup and then as a Zariski closed set, and then the set of all unipotents is just satisfying the equation x minus 1 to the n equals 0 if you are inside GLN. So that's a closed condition. It's a matrix equation. It will have n square, you know, if you expand it out, you will get n square equations. Whatever the number is, the structure, the exact form of those equations we are not bothered about. The point is that is a set of algebraic conditions, polynomial equations. Therefore, that defines the set of all unipotent matrices as a closed sub of closed sub variety, not of GLN. Okay, and GU would of course be G intersect GLNU, and therefore it would be closed in G because it is GLNU intersect G. GLNU is closed in GLN, therefore it would be closed in G. Okay, so the part that is true in general is that this is closed. Okay, but the rest are all special for the commutative case. Okay, and second, the map, if you take GS cross GU to G, this is the multiplication map. This is a subset, this is a subset, so it makes sense to talk about the multiplication map. Right, and this is a closed subgroup, so this is a linear algebraic group in its own right. This is a linear algebraic group in its own right. So you are considering this morphism of varieties, and this is an isomorphism of algebraic groups. So, and as was pointed out last time, so it is more or less trivial to see that this is an isomorphism of groups, right, with the commutative condition. And it is also obvious that the map is a morphism because it is just a restriction of the multiplication morphism. The non-trivial part is to show that and here is something new, so that's why I'm saying this point again. Unlike maybe in some other categories that you have been familiar with so far, just because you have a bijective map between two varieties, which is morphism of varieties, does not mean that the reverse map is a morphism of varieties. Okay, so so do you know an example of that when you studied affine varieties or commutative algebra? Okay, so here is an example that is relevant to algebraic groups. Okay, so let us take G to be an, okay, so let me define GM if I have not defined so far. Okay, so there are two very special linear algebraic groups denoted GM and GA. Okay, what is GM? GM is of course just K star. M for multiplication, A for addition. Okay, that's the logic for the notation. K star is all non-zero scalars of the underlying field K equal to K bar. Okay, so recall that we've always working with K equal to K bar of arbitrary characteristic, right? Okay. So you can also think of this as GL1, right? And another way to think about this is that it is the spectrum of K, T, T inverse. Right? Because this is an open set. This is what is called a principal open set in K. That is, so if you have an affine space, you might have seen the notation, and f is a function, f is a polynomial. If you have an affine space, n space, and you have a polynomial in n variables, then there is, the notations you might have seen are Vf and Df. Vf is the loci of solutions of points where that f is satisfied. Df is the complement. Okay, Df is therefore an open set in the Zariski topology. It's sometimes called a principal open set. Okay, now that is also it's an open set, but it's also an affine variety, because you can think of more generally. So this is how we think of GLN, for example, as a affine variety, because it is actually a principal open set in n square variables, because it is the points where the determinant the determinant function, which is a polynomial, does not vanish. Okay, so how do you, so DF, how do you think of this as a variety? Well, you can think of it as sitting inside an plus 1, right? So what is the map? So you have df is sitting inside an, right? So you send it to x here goes to x 1 minus let's see, let me put that. Okay, and what is the variety I'm thinking of here? I mean, so this goes, I claim, so df gets identified with So let me write so it's a principal open set, and it is that's one way of thinking of DF as a, so DF is open in AN, but it is also an affine variety in its own right by just making this construction. That's one way to think about it. Another way to think about it, if you wish, is just spec of K X and then adjoin 1 over F. Okay, you can also do that. Now, how, I mean, well, this and this are sort of the same, because how do you think of this? When I give you some affine algebra, how do you think of it? How do you think of it as a variety? Well, you take a polynomial ring. If you want to make it concrete, you take a polynomial ring, map it onto that algebra, and then think, and so you, by that means, by doing that, you will get some subset of this. You will take as many variables as there are generators of the algebra, right? And then you, so you will, by doing so and working through it, you will see that you can realize what the spectrum as a subvariety of as many in the affine space equal to as many variables that you took. Here, of course, you would take n plus 1, x1 through xn, you can take those, one more extra y, and you would map y to 1 over f, and if you work through it, it is the same as this. Okay, okay. So that's, I said that because this is like, that's what we have done. We put t and 1 over t, because you are inverting it is the d of t. K star is d of t, right? Because the points where t is non-zero. Okay, so does that justify that? Okay. Okay, so this is one of the basic algebraic groups, right? It's a commutative algebraic group. It's an example of this commutative linear algebraic group. Okay, now this one is K with addition as a group. Right, so it is just the, so this is just spec of, as a variety, it is just spec of KT. Okay, now here is the exercise that you should do. Write down the Hopf algebra structures on, see, what did we say? That the varied linear algebraic groups are the same as Hopf algebras with some property, right? Where the underlying algebra is a commutative, affine, reduced algebra. This is, so we've seen already that the linear algebraic groups and morphisms among them is nothing but the category of Hopf algebras, I repeat, where the underlying algebra is commutative, affine, and reduced. Okay, so that means these are examples of that kind. These are, of course, they are reduced, affine, commutative algebras. Okay, but now you have to make them into a Hopf algebra. Make them meaning the group structure here is inducing by that procedure of translation. There is a Hopf algebra structure that is induced on these two. Okay, so just to think through this, as an algebra we know what it is. How to add, it's just a polynomial ring. We know what it is as an algebra. It's just a polynomial ring that is just you're inverting 1 over t. You've localized at this element, right? You've made that into a unit. That's clear. What is not clear is what is the co-multiplication, right? So there is to make it a Hopf algebra, there is a co-multiplication and there is a co-unit. Question is, what is that? So write down. So write down explicitly that they are Hopf algebras is implicit because these are linear algebraic groups. But I would want you to write delta of t equal to, right? You should write that out. Write down explicitly the co-multiplication and co-unit maps on KT T inverse and KT. Yes, it will correspond to the maximal ideals in KT T inverse. Yes.
So that is a M spec. I mean, when you say spec, you are considering the. So GL1 is the M spec of KT T inverse, or?
Okay. 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 I was being. Okay, if you wish, let's see the way I set it up. Well, I am not obliged to write the M spec in the sense that I know that the spectrum map, see there is between reduced affine algebras on the one hand and affine algebraic varieties, there is one is the opposite of the other category. I am using that here. Okay, so yes, there is a little bit to be. So the point is, when I think of it as a, okay, so there is a little more here than meets the eye, correct? So and it would be worthwhile for you to. So what I'm trying to say is, if I didn't write the M spec, I'm not making a mistake. It would be all right without writing the M spec because. There is a correspondence that I go between from varieties to algebras and back, right? So so how do I think of the variety? If I just abstractly think of it as to produce the variety, I must just take a polynomial ring, map it onto, and then that will produce for me, and look at the kernel of this map, and then that look at the points where this is non-zero. That will give me the variety structure. That's correct. So in a sense, there is M spec sort of implied when you write spec. So I am not incorrect when I write spec, but your point is well taken that when I think of it as points, as an underlying group, or even when I want to think of the variety attached to a affine, reduced affine algebra in an abstract sense, then I should be taking M spec of this. That's the way in which I get the set of points without any specific embedding. Right? Okay. So indeed, you are right, but it is not incorrect for me to write without the just the spec without the M spec. Okay. Okay. So, but at least is the problem clear? Yeah. Okay, good. Okay. So I was going to give you an example of where you have a morphism, but the inverse is not it's a bijection. It's a morphism of varieties, but the inverse is not a morphism of varieties. So the standard example is, of course, so I'm going to give you one which is even an algebraic group morphism. It's even more. All we needed is, well, actually for this you have to, it helps because you might ask, okay, at the level of varieties you might have a map of varieties which is a bijection. One way it's a morphism, but the reverse is not a morphism. But maybe if you have algebraic group structures on them, and then you have an algebraic group bijection as a group morphism, then is the reverse a morphism. Even that is not true. The standard example is as follows. It's the so-called Frobenius map. So Frobenius map. So you take Gm to Gm, x going to x to the p. So this is characteristic of k equals p. Right? Now I claim this is a bijection. So this is just the, so raising to the pth power respects multiplication because you are in a commutative group. Right? Okay. Now it's a bijection because you are in characteristic P. Right? Yeah, so if it's on 2 because if you are an algebraically closed field, everything has a pth root. Okay? It's 1 1 because if x to the p equals y to the p, that will give you x minus y whole to the p equal to 0, which means x equals y. So it's a bijection. So it's a bijection, but what the map, so at the level of you must have a map right here. So if you have a morphism of varieties, there must be a morphism of algebras in the reverse direction. Okay. Furthermore, this is a map which will respect co-multiplication. It's a half algebra map, right? That you can check. But so what should T go to? So we can think like this. T is a function here. I pull back this function here. So but I take the composition. What does T do? What does T mean? I just see the point. I just map it to itself. So if I compose it, if I take x, it goes to x to the p, and then I map it to x to the p. So the map is x going to x to the p, right? So where does T go? That should go to the function T to the p. The pullback is T to the p. Okay. So, but this does not have a. If this map had an inverse, there would be an inverse in this direction. But you can't t to the p going to t to the 1 over p is not a, it's not possible. So this is a bijection morphism of algebraic groups but the inverse set map is not a morphism of varieties. Right? Okay. So the last part is not really, it's something you have to do. Okay? When I said last part, I meant GS cross GU to G, the multiplication map. The claim is it's an isomorphism of algebraic groups. Right? So what we said is clear, it's clear that it is an isomorphism as sets or groups. It is clear that it's a morphism. The content of that statement lies in you have to show that the inverse is a morphism. Okay? And there is you can't take recourse to some general statement there, because you have examples like this which shows that it could very well be that you have a isomorphism bijection which is a morphism of algebraic groups, but the inverse need not be a morphism. Okay? Okay, so so that's about structure of how a commutative linear algebraic group looks like, right? So theorem 3.1 you can think of as some kind of structure theorem for, or an initial structure theorem if you wish. You can write it as GS cross GU. So you can think of as GU as a unipotent group, GS as a group consisting of all semisimple, all elements are semisimple. Okay? So that's a kind of structure theorem for commutative algebraic groups. The next thing that we did was a sort of a structure theorem for algebraic groups in dimension 1. Okay? Okay. So if you want to, one way to think of things is by dimension, right? Of course, this gets very complicated beyond 2 or 3 already, but anyway, so we are going to talk about connected algebraic groups of dimension 1. So you might ask for dimension 0. What is a connected algebraic group of dimension 0? So what does dimension 0 mean? It is, as a variety, it is a set of points, right? It's a set of points. So there are quite a few of those, namely all finite groups will occur as algebraic groups, linear algebraic groups of dimension 0. But if you put the condition connected, then the only thing is a point. Okay? So there is connected algebraic group of dimension 0 is just a point. The next thing is connected algebraic group of dimension 1. Okay? So the statement, okay, so let me state 3.4.9. This, as I said, we are not going to prove this because the proof involves a lot of technical detail, which this might be one topic where some of you may want to read it up and present if such a thing is comes up. But I don't want to, like I was saying last time, I will only concentrate on 3.1 and 3.2, but we will state this now. right? We are not going to prove this. Okay, it's a simple enough statement and it might be attractive enough to try and prove, but it looks like I don't know of a simple proof. So G connected linear algebraic group of dimension 1. Then G is equal to Gm or G equals Ga. Nice statement, isn't it? Right? There are no others. Okay, let's see what we did prove. 3.1.3. Okay, so this is the theorem finally, but this is what we did prove. So G, same connected linear algebraic group of dimension 1. Then 1. Both these are commutative, right? So you must be able to show that it is commutative in the first place, which we did. Right? I mean, I repeat, the proof was non-trivial, at least at, like I said, at the level of this class. It is non-trivial. Okay. There may come a time when people will say, this is true. So they will quote this theorem as if it is an obvious statement. But even there is no, the point is there is no simple proof of that. Okay. Okay. 2, of course, in this case, all elements are semi-simple. In this case, all elements are unipotent. So either G equal to Gs or G equal to Gu. 3, if G is unipotent and the characteristic is bigger than is positive, then every non-trivial element of G has order P. That better be true, because see, if it is unipotent, it cannot be this. I mean, unless it is it cannot be this. It cannot be the trivial group. It is dimension 1. So it has to be Ga. Ga is K as an additive group. Every element there, if you multiply by P, you get 0. Right? So we see every element has order P. Right? So that will follow if you. So the thing to do is you should. This is the final statement. Okay, you should keep this in mind. But as far as how far we have proved it, we have done these things. Okay, so maybe let's see, where were we? Did we do this fully? So maybe let's look at this last bit. Okay, let's look at 3. So let's see. So you can put okay, here also there is something non-trivial, I suppose. So you can put G in GLN, right? Now it is unipotent, right? So so the images are unipotent here, right? Which means I can write G minus 1 to the n equals 0. Correct? Okay. Now choose P some power. So Q is equal to P to the sum H such that Q is bigger than n, bigger than or equal to n. Right? Then what do you get? G minus 1 to the Q equals 0. So that gives you G to the Q equals 1. So what have we proved? Every element has order up, so has order a power of P. Every non, right? Okay. Let's see, how do I want to show that it has a power of P? Okay, so he's so consider G P to the H So these are closed and connected. So let's put here, actually not every element has, it's more than that. Okay, it's more than that. What I know is that for some H, G to the P to the H by above. Okay, can you tell me why these are closed and connected?
Because you started with G connected on multiplication maps.
Hmm?
Under multiplication maps.
Hmm.
So it will be connected. G P bar H is connected.
Hmm.
And
So that gives you both. if you think of the map G going to G to the P to the H, G raised to Q, right? Now that's a morphism, right? Or from G to G, right? So the image is closed and connected, right? Okay. Now, so now I claim G to the P must be equal to 1. Why? Because it's closed and connected, therefore so implies why? Because if G to the P is not 1, then G to the P must be equal to G, okay? Because if not, right, because it's closed and connected, therefore it is either 1 or the whole group. So, and if the moment it is whole group, you cannot get to the trivial group at any step, but we have to get to the trivial group at step Q, right? Okay. So as you can see, while the statements, yes, Arghya. That is because you choose a Q which is beyond n, GQ equal to 1. G was arbitrary here, right? G was for all G. So thus G to the Q is equal to 1 for such a Q. Is this clear? Yeah. Okay. So see, I am going slow. I mean, we have just done 1.5 pages in the book, but I think there is a lot of subtlety here, and it's although the statement may look innocuous, you have to pay attention to. There's a lot of detail there. Okay, so I insist that you, and that is the course. In fact, that's part of the course. I insist that you understand the detail. Okay, and we have not used, we are not using any, we might have used 1.9.5 without proving, but there is nothing from chapter 1 about general varieties or anything that we have used. It's all. In other words, I mean, the proof is complete, perhaps modulo just that 1.9.5, which was of course used in many places. Okay, so there is you should feel absolutely comfortable with the proof. I mean, that is you should insist on that. That's a goal of the course. Okay. Now let us go on to the 3.2. Okay, so as I said, we've stated 3.4.9, which is sort of one of the main theorems of this chapter. Okay, we've done 3.1, which is a something towards this, and a structure theorem for commutative linear algebraic groups 3.1.1. Okay. Now we are going to define tori and prove some equivalent, some properties of those. Okay. And again here it will be even from a, there are things you will see that are interesting from just a group theoretic point of view, even from the point of view of finite groups. Okay, there are statements that you will see that if you could take that statement out of this linear algebraic groups and then put it as a statement in just in group theory, and it would be interesting. Okay. So here we make some definitions. That is the title. Okay, diagonalizable groups and tori. Okay. So what do you think a diagonalizable group? What intuitively, what do you think the definition should mean? It is what you think it means. If you just follow your nose, you will see the definition, and that indeed that's what it means. So what is a diagonalizable group? So what is a linear algebraic group? It's a closed subgroup of GLM, Zariski closed subgroup of some GLM. What should be a diagonalizable group? Diagonalizable linear algebraic group should be closed subgroup of the diagonal subgroup inside GLM. So in particular it must be commutative, because it's a subgroup of a commutative group. Okay. So a closed, that's what the definition will be. A closed subgroup of the diagonal group in some GLM. Okay. That will be and if it is connected moreover, then it's okay. Anyway, we'll come to that. Okay. So here are some general definitions which are interesting. So G linear algebraic group, as always. Okay, so what we'll do is we'll consider homomorphisms from G to GM. Okay, so now that GM is a commutative group. So when you have homomorphisms into a commutative group, you can, so G is any group. Let's say think abstractly. G is an abstract group, and you have you fix a commutative group, end group, meaning so if I consider from a group G to a group H which is commutative, homomorphisms. If you give me two homomorphisms, I can multiply them. That's also a homomorphism, because I can define phi times, can't I? So if I have G to HH commutative, if phi and psi are homomorphisms, I can multiply the homomorphisms. First of all, what do I mean by this? It's pointwise, right? G1, G2, if I write, I claim this is psi. Okay, so multiplication I have to define. I just say this. Now, this is my definition of pointwise multiplication. Now I have to show that this is this of course I can do this. I have not used commutativity of H. I am free to define this. But the problem will be that it won't be a homomorphism unless, if H is commutative, I can easily see that it's a homomorphism, not otherwise. So let's do it. So psi of G1, G2 is what? Is by definition now psi of G1, G2 So this is what I'm checking, right? So to say it's a homomorphism, I must check correct. This is what it means for it to be a homomorphism. I'm checking this. What is this on the one hand? By definition it is psi g1 psi g1. This on the other hand is psi g2 psi g2. What is this? This is, but these are homomorphisms, so I can expand that out. So psi g1 okay phi okay g2 psi g1 psi g2, but now the image is coming, all this is happening inside H, which is commutative. So I can take these two here and rewrite it as these two, if I got it right. Yes, indeed. So that is commutative, correct? Okay. So if you see, generally if you have maps to a ring, okay, I mean this is not in, you have to be careful while applying this principle, but I mean for example here maps to homomorphisms to a group, do they form a do they have a group structure, right? So here for example what I'm trying to say is, suppose I take maps from a set to a group, right? You can, by pointwise multiplication, there is a structure that comes on this set. You can just, if you have set to a ring, if you have a set of all maps from a set to a ring, then you can think of that as a, you can define an addition and you can define a multiplication, right? That's what you're doing. But here what we are saying is, if I start, I'm not taking arbitrary maps, I'm taking homomorphisms and saying that I can define the product, this part I can do in general, right? For any group. I didn't use any structure of H, but the point is, if H is commutative, the product is also a group homomorphism. It is not just any old set map from G to H, but a group homomorphism, okay? So is this clear? This is a general observation. So what we are going to do, so we have this commutative group, namely GM, right? Now what we want to do is, somehow this is a very special group and we want to look at all linear algebraic group homomorphisms from G to GM, okay? Now if I have arbitrary group homomorphisms, their product was a group homomorphism. Now, but here I am taking, suppose I take group homomorphisms which are linear algebraic group homomorphisms, then is their product a linear algebraic group homomorphism? Well, yes, because you can just, it's just like, because the product map is a morphism of varieties. So it's rather trivial to see that if I take the set of all linear algebraic group homomorphisms from G to GM, it naturally has the structure of a group, okay? So here, that with that introduction we will say, so a homomorphism of algebraic groups chi, so this again notation is standard, G to GM is called a rational character. if you were doing abstract groups, you might have seen this definition somewhere. So if I take a group, then maps to C star, group homomorphisms to C star are called characters. Okay, now the word character is used in many different senses in group theory, I suppose. I mean, character means a character as a representation, etc., etc. Now they are all related with each other. So this is yet another use of the word character. Okay, and why do we say rational? To emphasize that it is a homomorphism of algebraic groups. Okay, again, as I said, you have rational G acts rationally, we say, on a variety X. So you might want to say you might want to think it is polynomial rather than rational. But the correct word is, I mean, as I pointed out before, polynomial has been reserved for a certain special kind of thing. So the correct word to use is rational. So I hope it's clear. This rational refers to the fact that we are taking not abstract maps from G as an abstract group to K star as an abstract group, but those that are linear algebraic group homomorphisms. Okay, now X star G. So this is a capital X with an upper star, right? Why should you write a star above? Is because you'll see that it is a contravariant functor. So that's why it's written with an upper star. So this is, by definition, this is the group of all, group only as an abstract group. I am not putting any group of rational characters. Abstract abelian, abstract group of characters, rational characters of G. This is an abelian group. Because this is abelian because H is commutative, and it is written additively. So when we write chi1 plus chi2 of G, to mean chi1 so acting on G will be chi1G, chi2G. Okay. Okay, here is have you seen this before? Something called Dedekind's lemma. No? Okay, never mind. It's a very beautiful statement. This is it has nothing to do with algebraic groups, in the sense that it's a statement about abstract groups. It's a very beautiful statement. It goes by the name of linear independence of characters. Let's give it a name, because that's what it's proving. Linear independence of characters. It's one of those beautiful statements. Okay, it says the following: take an abstract group, take the multiplicative group of non-zero elements of any field. Right? Now I consider characters from this group G, abstract group G, to K star, which are just group homomorph, not just rational characters, just arbitrary characters. Rational characters are of course characters in particular. Now K star is of course sitting inside K, and you can think of these as functions from G to K in particular. Right? K star, you further think of it as putting inside K, and then all these will be in particular functions from G to K. The point is, if I take say 100 of them, I give you 100 characters, say. So functions from G to K is, remember, is a vector space, is a K vector space. Right? Because I can add and multiply, scalar multiply, add by pointwise. Right? Okay. The point is that they are linearly independent as elements of this vector space. So if as long as the characters are distinct, they are linearly independent as functions from G, as K linearly independent as functions from G to K. Okay? This is a very beautiful statement. So G abstract group K field so X star, so let me write abuse notation and use the same thing as here, but so this is equal to set of group homomorphisms, abstract group homomorphisms. From G to K star. Theorem is, the statement is that X star G is a K linearly independent set in Hom or morphisms, set maps in the K vector space set maps G to K. Okay? It's a nice statement, isn't it? Okay, so what's the proof? And the proof is also quite easy. It's just a few lines, although it's a tricky, but it's easy. It's short and easy, but tricky. Okay. Okay, so I have to show that a certain set, possibly infinite, is linearly independent. Okay, of course, but linearly independence is just it refers to showing that there is no finite linear combination, no non-trivial linear combination, finite linear combination. That's what you have to show. Okay, so let us do it. Suppose I have a single element, so it's just a question of 1, 2, 3 showing for. So let's proceed by induction. Suppose I have single element. To show a single element is not linearly independent, what do you have to show? That it is non-zero. right? So why is a character non-zero as a function from G to K? It goes to, so for example, chi of 1 goes to 1. See, you have to be careful because so it is it's not 0, right? That's what you have to show. This function is not 0, right? Why is this function not 0? Because 1 goes to 1. Okay, so proceed by induction on the number of elements in a non-trivial linear dependence relation among characters, among elements of okay. So let's call this on the number n, let's give it a name n. So if n equals 1, all I have to say is if chi in chi star G implies chi is non-zero because chi of 1 is 1, for example. Okay, let's do for 2. How do you do it? So I have to show, suppose I give you chi 1 and chi 2, which are distinct, right? They are distinct, that's all you know. Chi 1 not equal to chi 2. We want to show that there is no linear dependence relation. So let's see how to do this. So in a non-trivial linear dependence relation, right? So I can write chi 1 is equal to because non-trivial so both are non-zero, because if one of them is 0, then you are reduced to the previous case. So a1 chi 1 plus a2 chi 2 equal to 0. If one of them is 0, it will become chi 1 is equal to 0, which it's not true. Okay. So no, both are non-zero, and since both are non-zero, I can divide by 1 and write it. Now is that possible? Because right? Agreed? Okay, let's try n equals 3. So again, you can assume that they are all non-zero, because the moment one of them, so you have a non-trivial linear combination a1 chi 1 plus a2 chi 2 plus a3 chi 3 equal to 0. If one of them is 0, then you are done, because it is a non-trivial relation among smaller number of elements. So you are done, and so you can assume that all of them are non-zero. And once again, by multiplying by the inverse of the first coefficient, you can also always think of chi 1 is equal to a1, chi 1 is equal to a1 chi a2 a chi 2 plus b chi 3 or something like that you can write. Okay, so so chi 1 says a2 chi 2 plus a3 chi 3. You can write that. Right? Now I have to somehow obtain a contradiction from this, right? So let's see. See, left to yourself to think about this. I mean, what would you do? You would try to evaluate it at various values and try to get quite a few things about A1 and A2, right? That's what we did there. That was easy, but that's, you evaluated at 1 and you got some condition on A saying that it's A1. So you should think of, actually I'd recommend that you do it by yourself without recourse to a book. I mean, I can write down the one-line proof from here, right? In fact, you don't even need these steps. The books will just write the induction step, right? Assume n, and then you will get a non-trivial relation among n minus 1, and then you're done. Okay, so maybe I'll, not to break the suspense, I'll just leave it at that. Okay, maybe we'll come back and write down the proof next time, but for now I want you to go ahead and try and write out enough from there how do you finish this. Okay, so proof is postponed with the recommendation that you try it by yourself before looking at a book. It's not given in Springer. I mean, he just says by Dedekind's lemma, this is true. Okay. Now we come to the next theorem, which defines diagonalizable groups. Maybe there is a couple of more. Okay, so there is also the definition of a co-character. Which is, what is a character? A character is a morphism from G to Gn. A co-character should be a morphism from Gm to G. You might have seen one parameter subgroups in Lie groups if you have studied. So this is it's the same definition, one parameter subgroup. Okay, but there is a paragraph of definition here, but we'll worry about it when we actually deal with co-characters. Okay, so for now let's go on to but let me state the theorem, and then there is an example before the theorem, but I want to state the theorem and then come to the example. So theorem. So this is later. So what is a diagonalizable group? The definition is what we said it is. Diagonalizable LAG is equal to, this is the definition, closed subgroup of some Dn. Dn being diagonal matrices, diagonal invertible n cross n matrices. Right? This is a linear algebraic group. Why? Because it is sitting inside GLN, and it is closed because it is just the condition that all the non-diagonal entries are 0. Right? So that's a closed condition. So it's Zariski closed clearly. So it's a Zariski closed subgroup of a linear algebraic group, in fact of GLN explicitly given. Therefore it is a linear algebraic group, and we are saying diagonalizable linear algebraic group is any closed subgroup of this. Okay, makes sense, right? if you can make it all, if you could make it look like a set of diagonal matrices, it's called diagonalizable. Okay. Now here is the theorem. So this is the structure theorem for diagonalizable groups. Okay, you should think of this as a this is 3.2.3. So I would like to, so I call this structure theorem for diagonalizable groups. So far we have had a structure theorem for commutative linear algebraic groups, one structure theorem for dimension 1 connected linear algebraic groups. Now this is a third structure theorem for diagonalizable linear algebraic groups. Okay. The following G linear algebraic group. So the following are equivalent for a linear algebraic group G. 1. G is diagonalizable. 2. So you look at the group, the abelian group of characters, right? So far we have seen that this is a group. It is in fact an abelian group because it is just homomorphisms into GM, and we write it additively. That's the so far. So this is a finitely generated abelian group. And spans K G over K. So, okay, let's understand what you are thinking of each of them as it's a character, meaning it's a map from to K star, but you can also think of it as a map to K. Therefore, they are in particular, they are elements of KG, right? So they are as functions, since they have values in K star. In particular, they have values in K, and they are morphisms of variety. So they are actually functions that valid, that live in here, and they will span K. Okay. I mean, I understand that. Right now, I would suggest that you sort of follow it abstractly. In a minute, we will do an example which will be illuminating. Okay, you'll see it in action. But right now, even if it is a little, little abstract, because don't know how big X star G could be, or we haven't seen one example of an X star G. Okay, never mind. But abstractly, it makes sense, right? It's a group. It's a subset of KG. Right, that's the extra thing we are saying here, and as a subset of KG, it spans a K. Okay. Now, if it spans K, then what can you conclude using Dedekind's theorem? That it is a basis for KG. So you are only insisting that it's a span, but it will follow from Dedekind's lemma that it's actually a basis for G. 3. Any rational representation of G is a direct sum of one-dimensional representations. So if you wish, you can think of the third one as a representation theoretic characterization. Okay? The first one is a more embedding into a diagonal. That is one way to think. If every representation is a direct sum of one-dimensional representations, every rational representation. So it is what you would call, see, if you have a finite group and you take representations over characteristic 0, then every representation splits as a direct sum of irreducible representations, right? But that is only true if you take over characteristic 0. Okay, it's not true over characteristic P, even for a finite group. Okay, here what we are saying is that it is any rational representation is a direct sum of one-dimensional representations. Okay, in particular, so any rational irreducible representation should be dimension 1. Okay, that's what in particular it says. Okay, so we don't have time for to go to the proof, so we'll do it next time. But I do want to say a little. Let's look at an example. Okay, so can you give me a diagonalizable group? Look at that definition, closed subgroup of Dn. So I can take Dn, right? So example, G equal to Dn is clearly so what are characters? I have to verify. So for this, I have to somehow see that all three things are correct, right? Okay. So what are characters? So what do I want? So just think abstract group theoretically. I have a bunch of, so in a sense you can think of it's intuitively, at least intuitively clear that these, you can think of it as GM cross GM cross GM cross GM so many times, as many times as n, right? Okay. So if I want a homomorphism from here to K star, what can you do? Suppose I take up, give me one example, give me one homomorphism. But that's very complicated. Much more simple. Yes, it will work. Huh? Projection. Each projection is a character, right? Okay. So each projection is a character. What are other characters? So, and you can multiply characters. Determinant would be the product of all those projections, right? But you could have multiplied first with the second, right? Or you could have taken the projection and then inverted it, right? So these are some of the characters, right? Projections are characters. I can invert a projection, that's also a character. I can multiply projections, that's also a character, right? Okay. So so what is okay. So at least let's give this map. So if I give you some a1 through an here, integers, right? What is the corresponding chi? So let's call this a. This corresponds to a character is what I'm claiming. Now what does it do to an element? So chi a, what does it do to an element T1 through Tn? Well, it takes it to T1 A1, T2 A2, Tn An. Okay, and let us verify this. What is K of Dn? What's the ring of functions? Well, the projections are functions, but you can also invert the projections because they are invertible. You can take they're also valid functions. And if I take some, okay, so this is generated by, so claim is, I have used small t there, capital T here, so don't mind. I mean, the capital T and small t are the same. So, so this is equal to, notice, direct sum. So let's say over A in Zn of T1 to the A1, Tn to the A. That's a basis, right? If I have T1, say T1 inverse, what are it's the Laurent polynomial ring, right? So what is the basis? Powers of T are a basis, right? Okay, okay. Maybe we'll stop there with that example. Okay, so I'll see you on Wednesday. I hope the course is. Now it's time, if you have not already done so, to sort of spend quite a bit of time on the course. Okay, so see you on Wednesday next. And can we? Do you know the schedule for the exam? Okay, so next week, can you? I mean, it's fine with me if you don't. I can. So that week we are not supposed to have classes. Is that how it works? But maybe you don't have too many exams. Okay, so fine. So is it like next week is already? So next week we have to. It has to be clear, right? Okay, so by let's say then Wednesday, could you just check your schedule of exams and then we can, and also there are exams here, right? But I don't see any first year student here, so it doesn't matter. Okay, so see you.